Chapter 8, Lesson 4 of Advanced Algebra, and I want to combine now some of the things we've learned from the last two lessons to solve an expression like this. We learned from the last lesson that when we're asked to evaluate a logarithmic expression like this, to evaluate it, we do its inverse function, meaning we change it to its exponential. So remember, this means what is the exponent of 2? That will give me this value here of 16, and then I need to have the same bases, so I change this 16 into 2 to the 4th, because that's 2 times 2 times 2 times 2, and then once the bases are the same, then the exponents must be the same as well. So I evaluated the expression like that. Now in this lesson, what we want to do is to do the exact same thing. We're asked to evaluate this expression, but we can't evaluate it until we have it as a single logarithmic expression. Once it's as a single logarithmic expression, then I can evaluate it using what I learned in the lesson before. So we're going to take what we learned in this lesson about the properties of logarithms, change this logarithmic expression into a single logarithm, and then we're going to be able to evaluate it. So I'm going to take this expression first, and I'm asked to evaluate it. Before I can evaluate it, I must make it a single logarithmic expression, so I'm going to do that first. So this is going to be log base 2 of 4, and then minus means divided by. This value here is 16. And then I can reduce this fraction, so I have log base 2 of 1/4. Now that it's a single logarithm, I can apply the inverse function or change it to its exponential form in order to evaluate it. So going back to what we learned in the lesson previously, logarithm means what is the exponent of 2? That will give me 1/4. Now again, I need a base of 2, so I can change this to 1 over 2 squared, changing the 4 to a base 2, but in order to have the base in the numerator, I'll need to move that up. So I'll have 2 to the negative 2, moving that up, applying that property of exponents. Now that the bases are the same, the exponents are also equal, so this would be negative 2. So negative 2 would be this expression evaluated. So in order to evaluate a logarithmic expression, it must be a single logarithm. And if it's not a single logarithm, whoops, I don't need that. If it's not a single logarithm, I'll use the properties of a logarithm to change it into a single logarithm, which actually I did here, and then I'll use what I learned about evaluating from the previous lessons to evaluate that logarithmic expression. I'll do one more example where we're asked to evaluate this logarithmic expression, and again, I cannot evaluate it until it's a single logarithm and then apply the inverse function, changing it to its exponential. So I'll apply the properties of logarithms first. I know that this power property will make this a 3 cubed, so I'll remember that. I'll go ahead and write out the steps. So I'll apply the power property here first, so this would be log base 9 of 3 cubed. And then it's addition, so I'll make it a single logarithm, then I have 1/3 times then this 3 cubed. Okay? Now I can simplify this expression here, so I can go log base 9. Now I'm going to go over here. So this is 1 over 3 times 3 times 3 times 3. That's 3 cubed over 1. So this would reduce with one of those, leaving me 3 times 3, which is 9. So I simplified that multiplication problem. Now that it's a single logarithm, I can change it to its exponential form or use the inverse function to solve the expression or evaluate it. So what is the exponent of 9? That will give me 9. Now these bases are the same, so because the bases are the same, the exponents must be the same as well. So the answer for this expression is a value of 1. So this logarithmic expression evaluated is 1. And again, change the multiple logarithmic expression into a single logarithmic expression, and then apply what we know about evaluating, the inverse function, in order to evaluate the expression. Another type of problem that we'll want you to do in this lesson is where we give you the decimal approximation of 3 logarithms, and then we ask you to evaluate this logarithm without a calculator. Now, if we tried to evaluate this using what we know already about properties or about evaluating logarithms, we would change this to its exponential form, which would be 10 to what power is 24. Now, the problem with that is I cannot change 24 into a base 10. There's no power of 10 like we could use with those other expressions. So we'll want to use the decimal equivalent of one of these, or a combination of these values here. In other words, what I need to do is to change this 24 into a multiplication or division problem using these numbers here, 4, 5, or 6. So any combination of those, if I can change it into a multiplication or division problem, then I can apply the properties of logarithms. So I can change 24 into 6 times 4 because 6 times 4 is 24. So I can change this into 6 times 4. Now if I apply the properties of logarithms, that's going to be the log of 6 plus, because it's multiplication, the log of 4. And because I'm given the decimal approximation, then I can substitute in, well, log base 6 is 0.7782 plus the log of 4, which is 0.6021. It's simply now an addition problem here. Well, I'll add these numbers across. So it's going to give me 3, 0, 8, and then 3 and 1. So 1.308 is the approximate decimal equivalent of log of 24. So in problems like these, you're going to need to change this value here into some combination of these values over here so that you can apply the properties. Then it simply becomes an addition problem or a subtraction problem if you have division. So one more example here, we have log of 16. I need to change 16 into a combination of these values here. Well, 16 is the same as 4 times 4, or 4 squared. So I can rewrite 16 then as 4 squared, and now I can use the power property of logarithms, which means 2 times the log of 4. And now I know what the log of 4 is, so it's going to be 2 times 0.6021, substituting in the decimal equivalent or approximate, and so now it's simply a multiplication of this or just adding this together. And so that'd be 24012. So about 1.2042. So when you're given some logarithmic decimal equivalents and you're asked to evaluate, then you'll simply need to turn this value into some kind of multiplication, addition, or multiplication, power, or division of these numbers, and then you can simply apply the powers of or the properties of logarithms and then substitute the decimal values in, and then again it simply becomes from there an addition problem or subtraction problem.